Hi everyone, in this video we're going to be talking more about the standard deviation and using that to understand something called the empirical rule and the z-score. So this is a pretty big idea, but one that if you connect it to your life and the things you kind of think about every day, really we use this idea, then it's not too bad to really wrap your head around. And that idea is this idea of the empirical rule. And so you see this picture in front of you, in front of me. Now this, maybe you've noticed this and seen this before. This shape is called a bell curve. So something you maybe have seen before. In this scenario, we're calling it the normal distribution. When you see the word distribution, picture. So we could just think picture for now. So this is the normal curve, which also again is referred to sometimes as the bell curve. So this is really, really useful in statistics and is extremely common. And what this picture is trying to show you is there are many scenarios where we're going to have data, and that data, when you draw the picture, right, you put all the dots down, each dot is a piece of data on a graph like this, where then you're going to get this shape or something very close to it. And what is the shape trying to tell you? Well, the shape is trying to tell you that most of your data is kind of packed together in the middle. So, if you're thinking people, then most people, whatever you're measuring about them, are pretty close to the center, the mean being right here in the middle. And then as you start looking at values further from the mean, you tend to get less people there. So I think one that, an example that can help you with this as you kind of try to think of this is heights. So think of us trying to look at the heights of people. Just use adults. So we're looking at adult heights. So what you tend to see is, for something like this, is that most people are pretty close right here to the average height. Right in the middle is the average height, and most people are pretty close to that. We're going to talk about close and what that means exactly in a second, but just, eyeballing it, most people are here, and that's how you can see that in the picture is that this curve is tall. That means there's a lot of people in here. And then now just try to use your own intuition about this. Think about your, day to day. You go around, you're looking at people, you see people, and you see most people are around average height. But sometimes, every once in a while, you will see a person who's really tall. And think about that. The next time you see someone and you're like, whoa, they're tall. Then think to yourself, was I paying attention to the height of anyone else in the room? And most likely you're going to say, no, you weren't. Your brain uses this idea already. It uses this idea that if people have heights close to the middle, you're not going to pay attention to it. It's expected. It's usual heights. These heights are not triggering anything in your head to pay attention to. Your brain is seeing a person, seeing their height, storing that information, but it doesn't care, right? It doesn't care enough to alert you. Oh, look at that person's really tall. So you go around most of the time not even thinking about people's heights, but then you see a person who's very tall. So that would be like someone over here. And how is this represented in this picture? Well, you see that the picture, the curve here, doesn't have too much height. That's representing that there's not many people with that height. It's also far away from the average. The average is here, we're far away. And since I went to the right, that tells me taller because I'm getting bigger. Now, your brain is already set up to see a person over here and think, tall, like, wow, that person's tall. You also have your brain set up to see a person here and have it just register like, whoa, that person's much shorter than the usual average person. So this is not a new idea for your brain. Your brain does this all the time. It doesn't just think of the average as the actual one number. What your brain does, and what we're going to be doing, is your brain thinks, okay, based on my personal experiences or what I've read online or whatever, this is the average here, right in the middle. So this is the average. And your brain goes like this. Okay, but it's not just like one person is the average. I'm going to take an entire range of values as my average. So your brain does this where it goes, let me just grab all of these heights. And so again, I know these numbers are maybe a little confusing, so just ignore them for a second. But we're thinking of this as being heights. So to start, so this green box, and then every person inside this box here, our brain is going to think of as a usual height. It sees a person, so it doesn't. Your eyes do, of course, right? But you see a person. Their height, your eyes take in where they are, and then your brain calculates their height, tries to calculate their height, and then it compares that to this picture. And if that person is in the green box, it goes, yep, that's a normal height. All is well. I'm not even going to bring it up. And so you just go about what you're doing. But if that person's height is outside the green box, and where exactly is the green box? I mean, for each of us that might be different. We in this class are going to nail it down, what we want to be the green box and what we don't. But in any case, what your brain's doing is it's saying, okay, anyone in the green box, I'm not even going to think about it. Their height is totally expected. It's usual, nothing out of the ordinary. But if you get a person's height outside the green box, then your brain is like, oh, that person's really tall or really short. And I'm going to make a note of this. Maybe it comes to your conscious mind. That's it. That's the empirical rule, is we are going to write down a rule for what you already do. Right? We're going to write down a rule for figuring out what is expected, kind of what is really average, what is usual, green box, versus what types of information or data are unusual. And the reason we do this, you might stop and be like, well, why do I do this if my brain can already handle this? Well, it's twofold. So the reasons we do this are, number one, if we all have the same rule, life is better. So we all want the same rule. Now, it doesn't matter when you're looking at people's heights, but if we have two people both look at the same data and both kind of have this different ideas of what is usual or expected, that's not good. It makes it difficult to talk to each other, difficult to figure out how to solve things. So we don't want that. We want all to be dealing with the same rule. And then the second reason is, for things like height, it's not too bad to do this. But in general, our brains are kind of bad at this when the things we're looking at and numbers we're looking at aren't as obvious. So that's kind of a problem. We kind of stink at this a little bit. So we stink at this sometimes. So because of that, it just makes a lot of sense for us to say, you know what, let's just all write down the same rule and just use that. So that's what we're going to do. That's it. So that's the kind of like big overall idea of what's going to happen here. So there's a couple definitions here to read through, and some we've already seen. So a normal distribution. So this is a distribution. Remember, picture, picture, picture. So it's the picture of data where you start off with low frequency. This just means not many. Not many people are down here with this short height. Then you get lots of people in here at these heights. And then on the other end, you still get, again, not many people at these heights. And I'm just using height as my example. And we get a bell curve. So standard deviation, we've talked about this in a previous video. It's the spread, right? It's the way that we measure spread. And to be more specific, remember, we're taking each data point, comparing it to the average, the middle, and then we're trying to average those up. We're adding up all of those distances. So if you've got a lot of points that are far away, you're going to have a big standard deviation. If your points are all kind of centered near the middle, well, then in that case, you're going to have a small standard deviation. Right? So that idea still works. And so what does this picture then really say to me? Well, what this says, and the rule itself, the empirical rule itself, okay, is that, and we'll zoom down here real quick to talk about it. So the empirical rule itself says that, and this is all kind of together, usual data values. So just keep thinking heights right now if you need an example. Usual data values, or heights, are the ones that are within 2 standard deviations. So back to that example. If your height is within 2 standard deviations of the average height, then I want my brain to see you and go, okay, yep, your height is near the average, so I'm not even going to think about it. On the other hand, if your height is more than 2 standard deviations from the middle, the mean, then we want to collectively say, that's an unusual height. That person's really tall. That person's really short. So 2 is the cutoff that we want to use. And that's in this picture why I drew the green box at -2 and 2. These numbers represent how many standard deviations you are from the middle. So if I know the average here, and we'll do a quick example. Let's assume the average height is, let's see, 65 feet, probably like 67 inches. We could look it up, but we'll just guess. So let's assume this is the average height. Now, what if I knew that the standard deviation for heights, just as an example, was 3 inches? Like, well, what does this do? How does this help me? Well, this is it. This is all I have to do. The +1 means go up 1 standard deviation. The +2 means go up 2 standard deviations. The +3, keep going. Go down. -1 means -1, bleh, means go down 1 standard deviation. -2, let me get rid of this real quick. -2 means go down 2 standard deviations. I'm just subtracting here. Go down means subtract, go up means add. We'll do another example together so you can see it. You can kind of see it all come together. But that's the idea. If you're talking about heights here, you know the average, you know the spread, the standard deviation, then using this idea, you can pick out these numbers, and then we have a rule now that says if you are between 61 inches, so I'll extend this down here, and 73 inches in the green, we're going to say, yep, you have a usual height. But if you are shorter than 61 inches or taller than 73 inches, we're going to say you have an unusual height. And our brain's going to be like, oh, that's a tall person up here. Or down here, our brain's going to be like, oh, that person's short. That's it. That's the idea. And it's incredible how often you could measure something about a person just to stay with people, and you get this picture. It's everywhere in statistics. It's crazy how often you get a normal curve. And once you have a normal curve, you could set this up. Every time you get a normal curve, boom, I could set this up here. And these numbers here are helping us describe, exactly what we're expecting in here. So, for example, this first little box here, 68.26, what does that mean? That means that we expect 68% of people to have heights between -1 and 1 standard deviation. We expect about 68% of people to be between 64 inches and 70 inches tall. That's all this says. What's this one say? We expect about 95% of people to be between 61 inches tall and 73 inches tall. Keep going. We expect 99 and some change percent of people to be between 58 inches tall and 76 inches tall. That's the 3. That's it. So what you're going to be doing here is you're going to be trying to apply this idea to different scenarios, where in those scenarios I give you the average height, I give you the standard deviation. That's being given. So you're going to have to construct this and answer questions based on the percentages here and thinking through what it means to be usual, unusual. So we're going to see examples where we could do this with IQs, we could do this with anything where I'm looking at numbers, stuff like this. So this is the idea, right? So this is our idea. So the next thing that we get out of this that I mentioned at the top is the z-score. And so this might actually seem a little bit silly that we're doing this, but it's just a useful thing to kind of have in your toolbox. So the z-score, given a data value, so this is a key point. Each data value that you have, or any data value that you might want to think about, has this thing called a z-score. And this is all it is. Ready? It's the number, so I'm going to start right here. I'm looking right here. It's the number of standard deviations that your data value is from the middle. How many standard deviations are you from the middle? So if you had this picture, you could always eyeball it. Let me give you an example here. Let's say we have a new data point. So a little purple data point here. Okay, so where is my data point? Well, maybe my data point's right here. Well, eyeball it. That looks like, and just follow the picture, 1, 2 standard deviations, about 2.5 from the middle. So this looks like it's about 2.5 standard deviations from the middle. So that's what its z-score is going to be. That's it. The z-score here, then, the z-score would be exactly 2.5, if that's where I am. Now you can eyeball it, or you can actually calculate it, and the calculation's pretty easy. You take the data value. In this case, it would be a height. You take the height that you have, you subtract it from the average, which in this case would be 67. So in this case, we would get 67. And then the standard deviation was 3. And so you just plug in your height, your data value. And that's it. It tells you how many standard deviations you are from the middle. Now there's a little note here you got to think about. If you get a negative number, it means go left. Your height is to the left of the average. You get a positive, it means go right. So it's z-score. How many standard deviation jumps are you from the middle? And the reason that's useful is what we set up here with the green box. If your z-score is more than 2, you're in the unusual area with whatever we're measuring. If your z-score is less than -2, see over here, you're again unusual with whatever we're measuring. Okay? So that's the idea. That's it. Unusual data values. You're past 2 on the right, past -2 on the left. That's the whole idea. That's it. If you're usual, you're within the 2. Okay? And so this is the whole idea. And so you just got to keep remembering, like, this is already in my brain. It's pretty awesome that you already actually do this. And the first time that you are thinking about this and realize you're doing it is kind of fun. The first time, so just the next time you're doing something and something pops into your brain that you're like looking at or thinking about, I want you to say, especially about a person, I want you to say, like, wait, that thing I just noticed, have I been noticing that for all these other people? And if the answer to that is no, I want you to then think, why did I notice that height, that age, that whatever it is about this person? Like, why did I notice that? Is it because in my brain I'm putting them in this unusual zone compared to everyone else who's in the usual zone? And a lot of times that is what's happening, and it's pretty neat to be able to kind of see yourself do this without even thinking about it. It's a pretty cool thing. So if that's something that, happens to you, it's pretty neat. So let's see what it looks like to apply this. So let's go down to example 1 and see what this idea kind of looks like. So when you're going through this, there's a couple things I could ask you to do. So let's just look at this example. It says, Mr. Smith gives a test, and that test has scores that are roughly normally distributed. So the first thing you need to do is, when I'm talking about giving you data, you need to kind of look for this idea that the data looks normal. All that means, normally distributed, is the data probably kind of follows this picture. That's not the best normal curve you've ever seen, but the data points, if you graphed them, kind of look like this. About. So then what else do I give you? I give you the mean, that's important, and I give you the standard deviation. That's what we needed up here, right? That's what I said up here. You need the mean and you need the standard deviation. So then what I could ask you to do is to draw the curve for the class. I know it's a little crazy. You're saying, I don't know the test grades. How can I draw out the picture of all the dots? Well, this is the idea. If we know the general shape, you know the middle, you know the spread, we can construct the picture from that. It's not going to be perfect. I'm not going to draw the dots, but I can draw the general shape, and it should be pretty good. So we do that. All you do is you draw the curve, okay? Draw a nice little line here, and then what you have to do is you have to figure out where's the middle, what number goes in the middle, 1 standard deviation left, 2, 3, 1 up, 2, 3. And so let me show you what that looks like for this example. So we've got our test scores. Let me go down here. So you've got the curve. You could draw these lines in to help you kind of split things up if you want. Each set of these is important here. This is the middle. This is at 0 z-score. It is the middle. There's no difference between this and the middle because it is the middle. Now, next up, 1 standard deviation up. How did I get this? I took the middle and I added in 1 standard deviation. Remember, standard deviation was 10. How did I do the next one? I took the middle and I added 2 standard deviations. I go to the middle, add 3 standard deviations. How do I get this one? Start at the middle. Take away 1 standard deviation. Start in the middle. Take away 2 standard deviations. Start in the middle. Take away 3 standard deviations. So hopefully now you can kind of see with the way I'm doing this, there's a little connection here with the z-score number. So hopefully this isn't too terrible to see. See this -3? There it is. See the -2? There it is. See the -1? It's hiding, but there it is. 0, 0, +1, +2, +3. That's the connection between the z-score and the actual test scores, is how many standard deviations, 10s, did I have to go by to get to that value. And then you can mark things to kind of ground yourself. Remember, and this again just uses this picture, which we'll use every single time, 68% of the students score between 1 below, 1 up, 1 below, 1 up, 30 and 50. 95% of the students score between 20 and 60. 2, 2. 99.7% of students score between 10 and 70. 3 left, 3 right. Pretty amazing. We build this idea out from just knowing the middle and the spread. And now the scores don't necessarily have to perfectly fit this picture, but if you say that it's roughly normally distributed at the beginning, that just means that they should about fit this picture. And so we get all of this information about where our students are. Awesome. So there you go. That's this idea of kind of drawing this and thinking it through. But then what else could I ask you? I could also ask you to kind of talk through things like, what about a specific student? So like, okay, great, I did this picture. What the heck does it mean for the students? Well, one of the reasons we do this, or you could do this, is to try to give a grade, right? So, I give a test, okay? And let's pretend the test is out of 100, just to make things easy. Well, I might want to curve the test. This is where this would be useful. Maybe I want to curve the test. And so how would I figure out kind of how to curve it? Well, I would want to make sure that the people with the extreme scores on the right got a good grade, like a really good grade. The people closer to the middle got an average grade. And then the people on the left, they got lower grades, right? So what you do is you could use this idea to figure that out. Specifically, right, that green box we had before, that was this 95%. So if you were outside the green box, you got over a 60, we might want to be like, okay, that's really good, that's an A. If you're outside here, maybe we would say, okay, if you got over here, you got an F. In here, maybe you got like a somewhere between a C and B, and you could kind of go from there. So that's the way that you could kind of think about this, is you're getting what scores are really average, you're getting what scores are really excellent, you're getting what scores are really bad. You're figuring all that out by being able to kind of compare them this way. So we got an individual person here. They score a 63 on the test. Now, you might just hear that, okay, right? So you might just hear 63 and be like, oh no, that's a D, I didn't do well. But let's look up here. 63, where's a 63? So let's do this in a slightly different color. How about blue? So my student got a 63. If you're not seeing the scores and the picture, again, you're going to be like, oh, that's a D, that's not great. But look where they are. 63 is somewhere in here. That's 1, 2, more than 2 standard deviations away from the middle. That's an unusual score, and it's on the high side. So that person actually did pretty well. That's why this is so useful. It helps us really understand what a score means when we are comparing it to the whole, my entire class. So how would you calculate the z-score specifically? Take your score minus the mean, which was given as 40, divided by the standard deviation, and we got 2 and a little bit more. Boom. What about someone who scores a 38 on the test? What happens there? So let's grab them. Ooh, this is a nice color. That's not going to show up good though. What colors did I not use? Why aren't there more colors in the rainbow for me to use? This is ridiculous. How about this one? So how about a person who scores 38? Okay. Again, you're looking at that, you're like, uh-oh, 38, that's not great. And so, yeah, it's not a great score. But how bad is it really, right? Like, how bad is it really? Let's go back up. Find 38, right? 38 is my new score. It's actually right here. 38 is really close to the average, right? So even though that score, without looking at anything, sounds really low, if you're grading on this curve idea that we were just talking about, of like middle people get around an average score, maybe near a 70, people who are extreme on the right get the A's, people who are extreme on the left get the F's, then a 38 really isn't actually going to be too bad because you're really close to the average. Let's specifically write that down though. Let's actually get the score, right? So let's do it. 38, that's your score, minus 40 over the standard deviation. This number's really small, which tells us it's close to the mean. The negative part tells me that I'm below the mean. So I didn't quite hit the average, I was a little bit below, okay? But I'm still pretty close. There you go, z-score. So who has a better score on the test? Someone with a negative 1.8 z-score or a negative 1.2? And what test score did they receive? So this is me asking you the question kind of in reverse. But why don't we just use this picture and see if we can kind of just think about it and get it. So student 1, what happened to them? They have a z-score of negative 1.8. Student 2, they have a z-score of negative 1.2. So go find it on the picture. Ready? We're going to get to student 1 here. Okay? 1 standard deviation below. Why am I going below? Negative, negative. 2, not quite 2. Right? 1.8 is not quite 2. So this would be student 1. Okay, what about student 2? Well, we can do a slightly different color for student 2. Brown. So student 2, well, 1 jump, and I'm going to go only 0.2, maybe that's like right here. This would be student 2. Who got the higher score? Student 2. They're closer to 30. Student 1's closer to 20. So student 2 got the higher score. And we could just use the picture for this and the z-score. So although that's not too terrible to kind of think through that. But we also could just do the calculation because the z-score can be unwrapped to give you the value. So you've got to think of it this way. In the first 2 examples here, I took a quiz score and it's like I wrapped it up and gave you the z-score. Well, if I know the z-score, I can kind of unwrap this to give you the quiz score. I could just go backwards. So watch how we do this. Here is our z-score calculation. What do we know? Student 1, we know they got a negative 1.8 z-score. We know the mean of the class and the standard deviation. Got it? Student 2, negative 1.2, we know their z-score. We know the average. We know the standard deviation. Got it. Solve. It's not too bad to solve this. Move the 10 over. Move the 40 over. You get your score. So this person had a 22. So oopsie, made a little mistake here. The second person had the negative 1.2 z-score. They got a 28. So when we are doing this, we see that the person with a negative 1.2 z-score had a 28. The person with a negative 1.8 had a 22. And our prediction with who did better was right. There we go. And so I know there's a lot to this, but in terms of like the calculation and how the problems work, but really you just have to focus on this main idea to start. What's usual? What's unusual? How does that connect to standard deviations? If you are 1 standard deviation away, left or right, you're still in the average. You're still kind of in that normal, usual group. Up to negative 2 and 2, we're still going to say like, yep, that's fine, that's expected. You get outside those, start getting 3 standard deviations or more away, that's when we're starting to think like, that's interesting, that's an unusual blank. Height, quiz score, whatever. So try these out, try the computer homework. start looking at the written homework. Let me know if you have questions.